cosmic chameleon. It drives our universe by constantly changing form. It powers acceleration, expansion, and apocalyptic impacts.
Everything in our universe is energy. Your energy, trees are energy, the dirt is energy, and even the empty space between the stars is energy.
But where does all this ever-changing energy come from?
All of the energy we see around us every day actually comes from the very beginning of the universe, billions of years ago. When you see a car accident on the highway, that's a very energetic event. Cars get mangled, there's a big noise. But where did the energy come from? Well, the energy comes from the energy of motion of the two cars before they crash.
But where do the cars get their energy? From gas, a fossil fuel that gets its energy from plant life that was living millions of years ago. Plant life that got its energy from the sun, which gets its energy from nuclear reactions inside the core.
Those nuclear reactions get their energy from the particles that were created at the time of the Big Bang.
All the many forms of energy we see around us come from the Big Bang. The beginning of the universe.
The origin of all the matter and energy in the universe is really the Big Bang, the creation of the universe itself. Now, we think that, in fact, the Big Bang was the sudden expansion of a very small amount of space into a very large space, driven by a weird kind of an energy.
We're not sure what type of energy kick-started the Big Bang, but whatever it was, in one brief instant, it produced all the energy in our universe, past, present, and future. This is one of the most important and surprising aspects of energy. In black holes, exploding stars, or even power plants on Earth, it can be neither created nor destroyed. It can only be transformed from one type to another.
If the laws of physics in the universe never changed in the past and don't change in the future, then no energy can be created or destroyed. It can only be transformed.
Transformation is the key to how energy works. The universe is filled with many forms of energy, such as light, sound, thermal, and chemical. The most common among them is potential energy, the stored or pent-up energy of an object, and kinetic energy, the movement of an object. And all forms of energy are constantly converted into other forms of energy.
When you fire a gun at a target, you might think that once the bullet hits the target that energy is gone. But it's not actually gone. It's actually just been transformed into another type of energy. The chemical potential energy in the gunpowder has been converted into the kinetic energy of the bullet, sound waves, heat, and whatever energy gets transferred into the target, maybe causing it to move or explode.
Even the human body is a fine-tuned energy-transforming machine.
A good way to think about how we transform energy is eating. Humans eat a certain amount of calories every day, and then whatever physical activity they do that and burn off that certain amount of calories. And you have to continue to eat because you continue to be active and burn off calories.
Incredibly, Albert Einstein realized that energy and matter are really the same thing, and one can be converted into the other. That's the meaning of his famous equation, E equals mc squared.
Einstein came up with a way to explain that everything in this universe is energy. Matter is energy. If you weigh, say, 100 kilograms, that's your mass. And if you take that and you multiply that by the speed of light and then multiply that by the speed of light, then you get the amount of energy that exists within your body. Actually, about 1,000 times more energy is in your body than there was in the largest nuclear weapon detonated by mankind.
Objects may have the same amount of energy, but that doesn't mean they have the same amount of power. The key ingredient is how quickly the energy is released.
Power is equal to energy per unit time. So even something with a really small amount of mass, like say this cupcake, would have the equivalent energy of about 1,000,000 tons of TNT. We all know that cupcakes don't spontaneously explode and emit 1,000,000 tons of TNT. If I eat a cupcake, it only gives me about 200 calories of energy over several hours. Whereas if I have a stick of dynamite, that same amount of energy would be released in, say, 1,000,000th of a second. So the TNT has much more power, even though it has the same amount of energy.
If you have a pizza, and you're going to eat that pizza, say you eat 1,000 calories worth of pizza, that might be a big meal, but your body has to convert the matter of that pizza into that 1,000 calories. And it's really not that efficient. Take, for example, the same mass in TNT, or dynamite. When you light the fuse on that, you get way more energy.
All of the energy we use here on Earth to feed our bodies, power our electronic devices, and light our homes ultimately comes from outer space. Some of the most extreme transformers of energy are stars, including our sun.
At any given second, the sun is putting out about 10 to the 26 watts. That means a 1 with 26 zeros after it. That's like 400 billion nuclear weapons, all in 1 second. That's how much energy we're getting from the sun at any given second.
Stars, like our sun, produce many forms of energy. But it all began with gravity.
All gravity means is that we've observed that all matter falls towards all other matter. And it's interesting that you can use gravity to transform energy from one type to another. If I hold a rock up here, it has a certain potential energy. And then I let it go, gravity turns that potential energy to kinetic energy until it hits the ground.
Over 13 billion years ago, gravitational energy gathered up dust and gas to form the first stars. Once a star is formed through gravitational energy, it then produces nuclear energy.
Stars are powered by nuclear fusion. So this is when you take multiple hydrogen atoms and you smash them together to produce heavier elements like helium, or carbon and oxygen and nitrogen. When this fusion process happens, the enormous energy of what's called the strong nuclear force is liberated. And that is what lights up the star.
Nuclear fusion within stars, like our sun, then produces a form of energy called electromagnetic radiation. These are oscillating waves of photons, or particles of light. On Earth and in space, electromagnetic radiation consists of a spectrum of energy. On the low end are radio waves with low frequencies and very long wavelengths. On the high end of the electromagnetic spectrum are gamma rays with high frequencies and extremely short wavelengths. Each photon of electromagnetic radiation takes up to 150,000 years to actually get from the center of the sun to the surface before it can escape and head towards Earth. Luckily for us, our atmosphere blocks most of the dangerous wavelengths of electromagnetic energy, which are ultraviolet, X-rays, and gamma rays, from reaching our world. But it allows visible light, infrared, and radio waves to pass through. Light and infrared energies are absorbed by land masses and oceans, and then converted to heat energy.
The sun is continually emitting electromagnetic radiation, which is giving us heat energy here on Earth and in space.
Humans have found clever ways to harness the energy of the universe. We've learned to transform solar radiation into heat, as well as electrical energy.
One of the most common technologies we use to harness the power of sunlight is solar panels. Solar panels are usually made out of semiconductors, which are light sensitive. So when sunlight hits the silicon solar array, it generates charges. Those charges are then swept out of the semiconductor material, and that generates an electrical current.
Electricity can be generated from one solar cell or a solar farm holding 550,000 solar panels. And those currents can charge everything from a home to a hot sports car. Stars are awesome transformers of energy. Here on Earth, we're constantly bombarded with the sun's electromagnetic energy in the form of light. In turn, we convert it into other energies to power some of the most unlikely things in our everyday world.
We're here at Tesla Motors today to see how electromagnetic energy can be converted into mechanical energy, which is used to power this high-end sports car here. All it takes is simple electricity from your average wall socket. So if we plug the car in, like so, we're now taking energy from the wall socket and we're using it to charge up the car's battery. The battery, located right here, is used to run the car's electric motor. So the computer inside the car, which is right here, takes energy from the battery and uses it to turn the single electric motor, which powers the car at astonishing speeds, actually. So you can imagine if you had, say, solar panels on top of your house and you were to plug the car in, your car would literally be running off of sunlight. All right, here we go.
And transforming sunlight into electricity has its advantages. Electric vehicles accelerate faster than gas vehicles because electric motors provide full torque immediately, while gas engines have to rev up.
The Tesla here can do 0 to 60 in 3.9 seconds, and that makes it faster than just about any other production gasoline-powered car there is. This just illustrates the great power of electromagnetic energy. Isn't science fun?
Our sun is responsible for fueling almost everything in our world by transforming its energies from one useful form to yet another. Green plants convert solar energy into chemical energy through photosynthesis, which feeds all living things, including humans.
I get energy from my corn flakes because the corn in the flakes got their energy from photosynthesis of sunlight that converts sunlight into sugar, carbohydrates. All kinds of molecules have bonds between the atoms in the molecules that when they break, release energy and give us the energy that we need when we exercise.
And this life cycle of energy doesn't end here. Over millions of years, the decomposed remains of dead plants and animals are compressed underground and converted into fossil fuels. They come in many forms, including coal, petroleum, and methane.
When we burn oil or natural gas, we're really liberating the energy from sunshine that was collected by plants thousands, tens of thousands, hundreds of thousands of years ago and stored underground in fossil fuel repositories.
Fossil fuels are considered non-renewable resources. This doesn't mean their energy is completely destroyed, but that they can't be replenished naturally in a short period of time.
When we talk about non-renewable energy sources, like, say, burning fossil fuels, we don't mean that energy is gone from the universe. What we mean is that that energy source has been transformed into a form that's no longer useful, like, say, for example, waste heat.
The sun provides much of the energy essential for our survival. But this energetic powerhouse can also produce lethal energies. November 2006. NASA's Swift Observatory witnesses a frightening event. The largest stellar flare ever observed releases energy equal to 50 million trillion atomic bombs. The killer flare fires energy in the form of X-rays that would obliterate most life on Earth if it came from our sun. Fortunately for us, this radiation came from the star Il Pegasi, which is 135 light-years away. Even so, this incident illustrates the deadly energy being released from stars. including our sun.
A solar flare is a relatively sudden release of a tremendous amount of energy. This energy comes from magnetic energy. A bunch of tangled magnetic fields suddenly release this radiated energy. It can be thought of as a bunch of stretched, twisted rubber bands. That's the magnetic field lines. And eventually they just snap. And that snapping releases the energy and channels it outwards from a relatively localized region on the sun's surface.
Solar flares can reach as much as 15 million degrees because it's converting magnetic energy into heat energy, and massive amounts of magnetic energy into that heat energy.
Solar flares can occur several times a day during high solar activity. When they're erupting, each flare can produce as much thermal energy in a few minutes as the entire sun produces in 1 second. If some of the high-energy charged particles generated by solar flares are headed in our direction, they'll be deflected by another energy source, the Earth's magnetic field. It's produced by electric currents that flow in its molten core. These currents are hundreds of miles wide and move at thousands of miles per hour as the Earth rotates. This powerful magnetic field passes through the Earth and enters space.
The Earth's magnetic field stops or deflects most of the charged particles that come at us from the sun or from interstellar space. And this is a really good thing because it would be really bad for life on Earth if a lot of these very high energy particles made it to the ground and were to hit our bodies.
A massive star can send off flares for 10 billion years. And when the star nears death, it doesn't mark the end of the transformation of extreme energy. In fact, it's just the beginning.
Once you have the beginning of a star where it does start the nuclear fusion, then the nuclear fusion continues on and it will burn until all the hydrogen is used up, basically.
Deprived of the nuclear energy to support itself, a massive dying star finally collapses, igniting a supernova explosion. A supernova can radiate as much energy as the sun will emit over its entire lifespan.
Stars exist in a balance between energy from a nuclear furnace on the inside and gravitational pull of all the mass of it collapsing in on itself. And at some point when the nuclear furnace starts to die out, gravitational attraction becomes the final winner of that conflict. It collapses and it emits a bunch of light, and it's due to gravity overcoming the nuclear furnace in the star.
Now, it's important to keep in mind that the energy of an exploding star isn't simply created out of nothing. Again, it's energy that's transformed from one type to another. The core of a massive star collapses, releasing a lot of gravitational potential energy. That energy then is channeled into neutrinos, into the kinetic energy of the ejected material, and into the visible energy that we observe.
Supernovas are one of the most explosive transformers of energy in space. However, 99% of the energy released during a supernova is converted into something that's actually invisible to the naked eye. Strange ghostly particles called neutrinos. Neutrinos are nearly massless energetic particles that move at almost the speed of light and pass through matter virtually undisturbed. Every second, more than 50 trillion solar neutrinos pass through the human body without us knowing it.
The likelihood of one of them interacting with a particle in your body is so low that you don't notice it. And even if it did happen, it would be just a little blip of energy that your body gets, which is much less significant than all the other blips of energy it gets from other kinds of particles that are running into you, such as light or radiation that's naturally produced from the Earth.
Neutrinos were once impossible to detect. They traveled right through the Earth and exited back into space unnoticed. But in Hida, Japan, over 3,000 feet underground, lives the Super K Observatory. It houses a massive stainless steel tank containing ultra-pure water. It's been discovered that when neutrinos interact with the electrons or atomic nuclei in water, they produce a charged particle, which creates a flash of ultraviolet light.
As that particle streams through the water, it actually gives out a tiny blip of radiation that can be measured by those little light detectors, which then says that's a neutrino.
Could these stealthy particles be a source of energy here on Earth? That's what Alan Kay from Chicago, Illinois wanted to ask the universe. So he texted us, how can we harness energy from neutrinos emitted by the sun?
Interesting question, Alan. It turns out that neutrinos are incredibly hard to detect, so we probably can't harness the sun's neutrino energy. Also, we don't really want to, because only about 3% of the sun's energy is in the form of neutrinos. It's much easier to harness the sunlight, and there's much more of it.
Neutrinos may not be able to alleviate our energy crisis, but lurking in each galaxy exists a ravenous beast that just may be the most fuel-efficient engine in outer space. The ability to convert energy from one form to another has inspired innovative ideas for future space colonization. Supermassive black holes reside in the centers of most galaxies, including our Milky Way. They can store and unleash the energy of billions of supernovas.
When the supermassive black holes were forming, a tremendous amount of gravitational potential energy was converted into radiated light and other forms of energy. Because you had a lot of material get compressed into a very small volume. It had to give up a lot of energy.
A supermassive black hole is 10 billion suns worth. That means it has the equivalent mass of 10 billion stars, just all packed into a very tiny space.
January 2008, NASA's Chandra X-ray telescope unravels a puzzling mystery about the transformational energies produced by a black hole. It detects a supermassive black hole's powerful gravitational energy drawing in a nearby star. As the gluttonous beast gorges on the star, it spins wildly, sometimes approaching the speed of light. This kinetic energy twists up the gas and debris falling into the hole to form a fast-spinning rotational accretion disk. This rotating material is then released in powerful jets.
This extremely high energy material spiraling around the black hole creates a very large magnetic field. Now, some of the material actually follows those magnetic field lines and gets shot out along them, forming a big powerful jet that's sort of like a blowtorch.
Recent computer simulations have shown that if the extreme kinetic or rotational energy from a black hole's spin could be harnessed, these black monsters could become the ultimate galactic batteries.
Wouldn't it be great if you could have a spinning black hole just spinning there, out there in space, and you build this thing in orbit around it that extracts energy from that. And that would give you a huge amount of energy to fuel your super advanced civilization.
And black holes may not only be responsible for generating different forms of energies, they may serve a dual purpose as a galactic recycling center.
One might imagine an advanced civilization living near a spinning black hole. It could send garbage trucks close to the spinning black hole that would dump their garbage at the appropriate time. Those trucks would then emerge from the vicinity of the black hole with more energy of motion, kinetic energy, than they had going in. Those trucks could then hit a turbine, like a windmill, drive the turbine, generate electrical energy, and thus light up their cities. What a neat way to get rid of your garbage and solve your energy crisis all at the same time.
black holes may energize a future space colony. But scientists are now discovering that the energy from whirling black holes may be transforming into something dangerous. Cosmic rays are highly energetic charged particles. Contrary to their name, they're not rays of light energy. Rather, they contain very large amounts of kinetic energy, which can cause deadly effects.
Cosmic rays are way more energetic than anything we've been able to produce on Earth. Hundreds of thousands of times more energetic.
The most energetic cosmic rays are called ultra-high energy cosmic rays. They travel at close to the speed of light with ever-increasing brightness.
An ultra-high energy cosmic ray has about as much energy as a tennis ball hit at 100 miles an hour. That's how fast the professionals get them going on court. That doesn't sound like a lot of energy, but actually there are trillions of particles making up a given tennis ball. And what's going on is that you've taken all of that energy and put it into one subatomic particle. And that's what a cosmic ray coming in through our atmosphere is like. And so that's a lot of energy for a single particle to have.
New evidence suggests that galaxies, known as active galactic nuclei, may be the source for these ultra-high energy cosmic rays. These are galaxies that have super-spinning, supermassive black holes at their cores.
Those are essentially extremely powerful generators of energy. There are magnetic fields and electric fields all spinning around and throwing out particles at incredibly high rates, usually generated by a supermassive black hole at the core. And that sort of system, black holes especially, are able to produce huge amounts of energy that can throw out these particles in all directions.
Ultra-high energy cosmic rays have become one of the top health threats to interplanetary space missions. These charged particles could hurtle right through a spaceship and penetrate astronauts like tiny ballistic missiles, ripping apart DNA molecules and even killing cells.
A high-energy cosmic ray, if it interacts with human tissue, can do damage to the DNA in that tissue and lead to a disruption of the cell, maybe leading to cancer.
And cosmic rays may not only threaten space travelers. Every second, cosmic rays bombard our Earth's atmosphere. Some even penetrate all the way through and rain down on our planet. The key to cosmic rays' transformational energy is speed.
So even if it has really tiny mass, like most cosmic rays, they've got enormous velocity. So their kinetic energy can be really, really large.
When they strike the Earth's atmosphere, they collide with molecules, mainly oxygen and nitrogen. This produces a storm of energy in the form of ultraviolet radiation that cascades down on our planet.
Those cosmic rays are coming from outer space all the time, 24 hours a day, just impinging upon the outer atmosphere and running into the air molecules, and then producing showers of particles that we can detect here on the surface of the Earth.
Fortunately for us, one original ultra-high energy cosmic ray spreads its energy out to millions or even billions of particles. So its energy, originally in the form of X-rays and gamma rays, is so dissipated that it's no longer harmful to humans. However, these cosmic rays could cut off your cell phone conversation.
These air showers, as they're called, which are produced by the cosmic rays hitting the outer atmosphere, those could affect electronics here on the ground. Our computers and cell phones and other devices that we use every day are becoming more and more delicate as we miniaturize our circuitry. And that actually makes it much more sensitive to being disrupted by cosmic rays.
In every corner of the universe, we witness the destructive nature of energy in motion. Yet here on Earth, we generate a unique form of energy that comes from the creation of our solar system. Since the beginning of time, energy has been the universe's long-standing magic act, constantly changing from one form to another. One unique type of extreme energy is the legacy of our solar system's creation. Geothermal energy comes from the heat created in the Earth's rocky core, which exists about 4,000 miles below the surface.
Our solar system was first formed about 4.5 billion years ago when a cloud of gas and dust condensed to form the sun and all of the planets. A small fraction of that gas and dust consists of radioactive elements like uranium-238 and thorium. When the Earth condensed, some of those radioactive elements got collected into our Earth's interior. As those elements slowly decay over billions of years, they heat up the interior of the Earth. We can access this heat energy as geothermal energy.
Some areas of the Earth's surface allow this geothermal energy to seep through, such as near plate tectonic boundaries, volcanoes, and geysers.
Geothermal energy can be tapped near plate tectonic boundaries where this hot stuff comes up, produced by exploding stars long ago that are radioactive and release their energy over timescales of billions of years.
Geothermal plants around the world harness heat energy from superheated reservoirs to create electrical energy. Here's how it works. High-temperature, high-pressure water is brought to the surface, where it enters a low-pressure chamber and flashes into steam. The pressure created by this steam is channeled through a turbine, which spins to generate electrical power. Once the steam has exited the turbine, it is either released into the atmosphere as water vapor, or it cools back into liquid water and is injected back underground.
In almost all cases until recently, geothermal power plants have been either near plate boundaries or hot spots, weak spots in the Earth's crust through which the hot magma can come. So since most of the Earth's surface is not near a plate boundary, it's been relatively difficult to tap into geothermal energy.
The best concentration and quality of geothermal energy exists where there are high levels of tectonic and volcanic activity, like the Ring of Fire, which circles the Pacific Ocean. But excavating close to plate boundaries is tricky.
To get a lot of consumer energy out of the geothermal energy of the Earth really requires digging quite deep to where the temperatures are high enough that you get a lot of energy out. The technological challenges for extracting geothermal energy for consumer use are huge. You either need to harness a volcano or drill down very, very deep into the Earth, or cap the geysers of Yellowstone.
But this type of thermal energy may not be exclusive to planet Earth. Io, one of Jupiter's 4 main moons, has active volcanism like Earth. But the thermal energy from its core is produced not through the decay of radioactive elements, but rather through tidal heating.
Io has an elliptical orbit around Jupiter, so sometimes it's closer to Jupiter than at other times. When it's closer to Jupiter, the tidal stretching of Io is greater than when it's farther from Jupiter. So as it orbits Jupiter, Io sort of squishes back and forth. That gives rise to a lot of rubbing of the interior rocks, and they then release energy. The interior gets hot. Magma flows to the surface, and you see a bunch of erupting volcanoes. So that can be thought of as a geothermal energy.
We certainly know that the inside of Jupiter's moon Io is molten because we see volcanoes there, and that is the equivalent of geothermal. I say equivalent because geo means Earth, so strictly speaking, geothermal is Earth's interior energy.
Planet Jupiter may not have a molten core like its moon Io, but the gas giant's hot interior generates another form of extreme energy, wind.
The giant planets, Jupiter and Saturn, have very windy atmospheres. They are very stormy, not just because of heat from the sun, but in fact largely because of heat generated on the inside. Their interior parts are still contracting, releasing gravitational energy and converting it into energy of motion of the atmosphere, winds and storms. This is another example of the conversion of one form of energy into another. Some of the winds on the giant planets can travel at immense speeds, 600 or even 700 miles per hour. Now, most of them are only a few hundred miles per hour, which still is big compared to even big storms on Earth. But the fastest storms can travel at 600 or 700 miles per hour. That's really fast.
Earth also benefits from wind energy, but its source doesn't come from its core, but rather directly from space.
The source of energy that we see in winds on Earth is really solar heating. The sun heats different parts of the atmosphere by different amounts, and that causes imbalances that allow the air to flow. That's wind energy, mechanical energy coming from the sun's electromagnetic energy. That wind energy can then be used to drive a turbine, converting it into electrical energy that lights our cities.
Energy has propelled the evolution of the universe since its birth over 13 billion years ago. But now, science has discovered a mysterious type of energy that just may be the cosmic Grim Reaper. Throughout outer space exists a phantom energy. We don't know where this mysterious form originated, but it's now believed that it could destroy life on Earth, and maybe even the universe itself. In the 1990s, astronomers used the Hubble Space Telescope and other observatories to measure the distances of exploding stars in other galaxies. To their shock, they noticed something quite peculiar.
Recently, astronomers have discovered by looking at the distances of supernovae that the universe is actually accelerating apart. It's not just expanding, but it's actually accelerating. Some mysterious energy is driving the universe apart faster and faster.
Astronomers realized that the expansion of the universe is speeding up with time due to dark energy, a strange form of energy that exists everywhere. It accounts for almost 75% of all mass and energy in the universe.
And it's one of the big mysteries of the universe. It is in fact the biggest mystery of the universe in some sense, because dark energy is the largest component of the energy budget of the universe.
Our current knowledge and understanding of dark energy is very limited, even though dark energy comprises almost 75% of all matter and energy in the universe. It would be similar to us having only explored the landmass on the Earth when the ocean comprises almost 75% of all of the surface of Earth. We are just now starting to explore dark energy.
Scientists had once thought that gravitational attraction would cause the expansion of the universe to slow down with time.
The belief was that the universe was expanding from the Big Bang and that gravity ought to be slowing that expansion rate. And the big question at that time was, is gravity strong enough to pull everything back together? But we got a surprise. Gravity wasn't slowing down the expansion. In fact, when we observed carefully, we discovered that the expansion was accelerating.
While gravity binds planets, stars, and galaxies, dark energy appears to stretch the fabric of space and time, thereby pushing galaxies apart. Recent observations have shown that dark energy is causing our universe to expand at an ever faster pace.
Over the history of the universe, the relative amounts of dark energy and regular gravitationally attractive matter and energy have changed. Early on, regular gravitationally attractive energy dominated. And that's because objects were close together. There wasn't much dark energy in between them, so its cumulative effect was very small. But as the universe expanded and galaxies got farther apart from each other, the amount of space, all of which was filled with dark energy, increased. Let's suppose we model the universe as an expanding loaf of raisin bread, where the raisins are the galaxies, they don't expand, and the dough is uniformly filled with yeast. That's like the dark energy. Now suppose we continue to inject yeast into the baking bread as it expands. It'll expand faster and faster with time, because there's more and more yeast. It'll be accelerating in its expansion. In a similar way, with time, there's more and more dark energy in the universe, thus accelerating, speeding up its expansion.
If dark energy continues to speed up the expansion of our universe, we could eventually experience the Big Chill. Clusters of galaxies will spread thinner and thinner. Galaxies will exhaust their gas supply to form new stars, and old stars will burn out. The universe will become dark and insufferably cold.
In a universe that expands forever, or nearly forever, eventually the sun and all the other stars will burn out. They'll use up their nuclear fuel. At that point, there will be basically no source of energy for life on Earth. So life as we know it will cease to exist.
But if this grim scenario happens, all the energy in the universe won't disappear, because our energy budget has been fixed since the Big Bang. However, the energy will become impossible to access.
The energy gets spread out so much and diluted to such an extent that it is no longer usable.
But there are other theories about the fate of our universe's energy. In the distant future, some propose energy could be transferred to another place, perhaps another universe.
According to the laws of physics, energy can't be created or destroyed. And all the energy that is within our universe has always been here and will always be here. But what if a wormhole or something opens up to a parallel universe and bleeds off some of that energy? It's possible that our universe would start cooling off because we're leaking at that point. And I don't think that would be a good idea, because eventually the universe would cool off to a point where everything would freeze out and life wouldn't be able to withstand that.
We don't know what the far future holds for energy in our universe or beyond. But for the time